everyone. Thank you for being here today. Today is the second webinar of the ORION webinar series, and the topic for today is AI, sensors, and predictive maintenance in renewable assets. We will now begin the session with our project coordinator, Stine, who will do the introduction. Stine, you can take the control of the screen.
I am Stine Wilhelmine Holm, and I'm the coordinator, as Josipa said, in the ORION project. I work at SINTEF in Norway, Oslo, which is one of the Europe's largest independent research organizations. I'm happy to welcome you all to this second out of 4 webinars in the ORION webinar series. The webinars are part of the Sustainable Energy Days, which are events held during the European Sustainable Energy Week, where the goal is to raise awareness and promote clean energy initiatives. Today's webinar, AI, Sensors and Predictive Maintenance in Renewable Assets, explores how AI, SCADA analytics, advanced sensor technologies, and predictive maintenance are improving the reliability and cost effectiveness of renewable energy assets. But I will start by giving you a short overview of the ORION project. ORION is a 3-year research and innovation action, started 1st of September 2024 and ends by the end of August 2027. The budget is 3 million euros, and we are 14 partners spread over 9 countries and 4 continents. This slide shows the concept of the ORION project. We have 5 breakthrough components in the project, which are the sensor technologies, data and models interoperability, asset management, data-driven decision systems, and finally, the human-centric digital twin. In ORION, the digital twin will integrate the digital components and then empower better informed decision-making for the stakeholders, including policymakers, allowing them to share insights in a collaborative and virtual environment. This will help to address the stakeholders' needs in a comprehensive manner and will include the latest knowledge and best practices from the existing EU platforms and initiatives like Enershare, GaiaX, and Fireware. The modular toolbox of digital breakthrough components. The modular toolbox of digital breakthrough components will be tested and validated in 5 use cases. We have a Cape Verde/Norway use case on decarbonization of port cities. We have the Iberian use case on operation and maintenance of large PV farms. We have the Slovenian use case on operations and maintenance on floating offshore wave energy converters. We have a Brazilian use case on distributed co-simulation infrastructure, connecting real-time simulation in a support of a digital twin. And finally, we have the Canadian use case, focusing on modeling, monitoring, and reliable operations of energy generation and power electricity systems in Canada. I will now change slide. In today's webinar, Tatiana Guedes from Inês will tell us about turning asset data into maintenance intelligence. Then Miguel Mendes from EDP R&D will talk about real-world operational and maintenance challenges in operating large solar parks. Anja Diaz from SINTEF will present advanced sensing for offshore renewable structures. David Volk from Sigma Energy will talk about offshore wave energy and demonstrate condition monitoring in practice. And finally, we will hear from Dr. Benjamin Adrian from Fraunhofer. He represents the INTEREST project, which is a sister project of ORION, and he will share their work on how to predict remaining useful life under variable load profiles and maintenance activities. And after all the presentations, there will be time for a Q&A. And by this, I will give the word to Tatiana Guedes from Inês.
Thank you, Stine. Let me give the control. Let me request. Can you see my screen?
We can.
Yes, okay. And when I change, okay?
Yes, we see it.
Perfect. Okay. Thank you. My name is Tatiana Guedes. I work with a team of research from Inês in the ORION project. We are developing some solutions using AI to support the maintenance process and the decision maker in large PV power plants. Okay. The first point that I'd like to share with all of you, and I think it's important to understand, it's the challenge related to work with large power plants. When we are working with large power plants, we work with a large amount of operational information coming from several different equipments and locations. Okay, so it can make complex to define, identify the correct problem in the plant. The first solution I'd like to talk about, try clicking. I didn't understand, Miguel.
No, sorry, it was it wasn't you. Just keep going.
Okay, but you can see the slides correctly. Okay. Okay.
Yes, it's
okay.
from SCADA data to fault indication.
Okay, perfect. The first solution I'd like to talk about with you is a solution with the proposal is analyze the SCADA data we have access. Okay. And with the information here, we can understand better the behavior patterns for each type of failure and to find the correct fault indication to the maintenance team. Okay. Let me try here. I'm trying to change. Okay. But how AI can help us with this? Once we understand in this operational data the behavior related to each type of failure, we can train the algorithm and the AI solution to understand, to identify the fault signatures. What we call fault signatures is exactly we talked about last slide. Each type of failure has some behaviors in parts of plants that we can identify the failure, the location where the failure happened, and the type of failure. Okay, with this we can have a fast diagnosis, and we can support and we can send and create some recommendations to maintenance support. Okay. Based on this, in the ORION project, the proposal is use the dataset that we have access from SCADA, from the Iberia use case. With this, we can understand the behavior of the plant because we have access some electrical measurements. The failures that we are working is electrical failures. We can understand the behavior of the plant with analyzing electrical measurements and understand the behavior of the situations out of normality. With this, we can use in the ORION case, we can use a GNN, a graphical neural network-based model, train this model with this behavior, with this to identify these signatures, and give us information that we can use to create a recommendation to the maintenance team. So the first part that we talked about, where we have a large amount of data that can be very complex or confused to identify the correct failure, we can use it using AI to identify specific behavior and give us information to provide information that can be transformed in action. Okay. In the case of the algorithm that we developed for the ORION project, the proposal of the model is work with a dual diagnostic output. What it means? It means that in the same algorithm, we will have the same output. We will have the location that we can localize it and the classification of the failure. It's not only we have a failure with the characteristics of open circuit, a short circuit, contact or a ground problem in the ground. We can tell exactly the point where we have this problem. In the inverter 10, for example, in the inverter 21, in the string 8, we have a lot of options because it's a large plant. But the proposal here, using this workflow, is in the end supply the information of the detection when the failure happened, where the fault location, and which type of failure we have, the classification. Okay. So for this, in the ORION, we use graphical neural networks. Okay, and we have a sequence of filters and approach to have this output. When we talk about signatures of the failures, for different failures, we have different scenarios. For example, we know that we have some failures where the analysis in the time domain is sufficient to detect and interpret the event. Okay, if you analyze using the time domain, we can see before the action of the protection how the plant work and which type of change we have in the place of the failure. Okay, but we have some types of failures that the behavior is very similar to a situation of no fault, or similar between different types of failures, mainly in the situations of sunset and sunrise. And sometimes it's very complex to identify in sunset and sunrise some types of failures. But after some analysis, the researcher that developed the algorithm identified that, actually she's here, Yuang, identified that when it's hard to identify in the time domain, sometimes if you work with signal processing, we can identify the difference in the frequency domain. We can see better the difference in the frequency domain. For example, here we can see the blue and orange. Here we can see the difference. In the time domain, we have problem. Why it's necessary different approach to analyze? Because when we work with fault detection, it's good to have a good accuracy. And in the first development, we had an accuracy for about 70%, and it's not good accuracy. And now you can see that we have an accuracy more than 90%, include some filters like this one, and change some structures. Here is a first result, actually not a first, because we worked a lot to increase the accuracy, okay? But here is the results that we have using the data from a smaller plant than the Villa Castin that we are using now. In here we can see that it's a little small, but we can see that you have a good accuracy after some change. Okay, so an important thing that is, I think, is good to highlight here is when we have fast diagnosis, it's the resistor of the failure is better. And more important than the resistor of the failure is we can correlate the resistor, the moment when the failure happens, with the behavior of the plant. So when we understand what happens before the failure, we can start working with predictive identification, okay? And we can train and improve the algorithm to work with the pre-fault dynamics too. And this is a good gain. Okay? To give for the team, the maintenance team, something to help to decision making, the proposal is based on the output of the machine learning algorithm. We have the fault identification with the correct location, okay, and we can include some informations to based on the classification that can provide information about the severity. How this type of failure in this location can impact on the plant, and how the confidence of this information. And this can create a group of recommendations to action. Okay, and the other question that we can think about, but how the user can access this information, the output of the machine learning. One of the options is the use of the graphical digital twin. This is an example of a great work developed by our partner AUGM is a graphical digital twin where we can visualize the point where the failure was detected. And we can have some information here. Okay, here we can zoom in, zoom out, and etc. Other tool to access this information is the use of LLM model. We developed an interactive digital twin with LLM model support. How this can work? Here in the graphical digital twin, the user will have access to an interface and can access this LLM model, where can access the plant digital twin, the SCADA database, and the OEM knowledge, and can have interactive diagnosis, anomaly analysis, and report generation. So the proposal here of the LLM is not work in the identification of the failures, but is first supports the communication and knowledge retrieval, and make the interaction between the user and the solutions developed more user-friendly. Okay, this solution was developed in blocks, in modules, and here the proposal is the solution receive the question of the user, identify the intent of the user, and access the specific function that the user wants to use, because you have different solutions and different functions, and give for the user a contextual response. With this, the user can generate data, can, using the digital twin, can request or analyze the fault analysis, and can work with the knowledge retrieval model. Okay, only to use it like an example. Here we have the interface. This is under development. But here we can see that with this interface, we can, for example, understand about the failures that the machine learning algorithm detected. We can understand if the failure is the first time, or in this month, how many times we have these failures, or the behavior before the failure, or some questions like this one. We can understand, for example, in the case of this failure, what the user can do about it, okay? And can access in the database a group of informations that are available in procedures and rules, okay? So to finish, the proposal here is in this presentation is share with you that using AI and with the development of solutions using AI, sometimes some information that's very complex to have to analyze a database, we can have a fast diagnosis, better records, and maintenance intelligence. Thank you.
Yes, our next speaker is Miguel from EDP.
Good afternoon. As I said, my name is Miguel Mendes, and I work at EDP R&D. Within ORION, EDP, among other things, is supplying PV park data. And my department specifically is also developing some machine learning models for fault detection in power control systems. So this next section of the webinar will focus on some of the concrete challenges that O&M teams face, why these issues are important, and their consequences. And we'll also go over how we can use machine learning models in order to predict when said issues occur before they happen. So lastly, I'll also briefly explain how we can translate these outputs into actionable results to be used by the O&M teams. So in this slide, I have subdivided component level problems at a renewable power plant into three illustrative categories. The first one I called component degradation and refers to issues which affect energy production, but don't necessarily stop it altogether. So frequently these issues are capable of being modeled either through physical or empiric or even hybrid methods. Therefore, they are usually corrected or fixed during planned maintenance operations, which can even be scheduled a long time in advance. So as examples, we have soiling in PV parks, or even blade erosion in wind farms. They are good examples of this first category. The second category, component malfunction, refers to somewhat more severe challenges. Although these issues can cause some gradual decrease in performance over time, just like the previous category. For these challenges in particular, after a critical point, the component effectively breaks, causing the entire system to shut down. When this happens, as is the case with many electrical equipments, such as inverters or power control systems, the faulty components must be replaced or fixed before resuming normal park operation. The last category refers to mostly external problems, which are usually hard to predict events because they involve sources that are usually outside of our control. So example, situations where we have low wind or cloudy skies. These situations are external problems that we can't necessarily address directly. Nevertheless, even if we can't reliably alter them or in some cases even predict them easily, we can still detect them and know when they happen, because they directly affect our outputs and directly affect the data that we are receiving. So in this, so basically for the rest of this short presentation, I will mostly focus on the second category of issues. And basically the underlying idea of what we're doing is that these component malfunctions have a critical point after which they break, yes, but we can use fluctuations in the data we're monitoring before that happens, an indication of a potential fault that will appear. So basically we want to discover early signs of faults and predict them in the short term. Speaking of short, these faults can generally be this prediction be either in short term or long term. Long term fault predictions usually estimate more so the average time between faults, which helps schedule O&M at a macro level. And it also is a useful tool to, for example, establish contracts for fixed interval maintenance, while short-term predictions, on the other hand, are key in a different area. So as one can imagine, urgent requests or urgent anything really have many implications, both in terms of direct purchase costs of the equipment itself, but also indirect logistical costs such as travel, which frequently for these parks is in remote locations, which also brings up many sorts of different issues. Also, not to mention, we have to take into account effectively the cost of opportunity, because if the equipment is offline for a great period of time, we're also losing a lot of revenue. So we need to balance this out. And basically, both types of these predictions are important because stability and reliability of power is valuable. It has actual monetary worth. So how do we actually predict faults? As alluded to earlier, we can analyze the data we have at our disposal, measures such as power, voltage, and current at the different component levels, and forecast what these values will look like a certain number of days from now. So from there, it can be easier to determine if the equipment suffered a fault or not. So if in X days from now the power is at, for example, 10% of what it should be, then likely there is a fault at play. To do these predictions, we have multiple models that can be used, so only some of which are pictured here. And each one has advantages and disadvantages, either at the architectural level or in terms of the actual accuracy of the results. Albeit in this last case, sometimes it can be hard to know in general which model will perform better, I guess, for the general case. These models here are all used for forecasting. So basically to determine the evolution of these key variables over time, which is again, it's key in determining faults ahead of time. After forecasting, you may also need to develop classification techniques. And here, it also depends on a case-by-case basis. For certain components, certain manufacturers already suggest guidelines in order to detect some faults. However, if there are none, or if you believe or if the accuracy if the methods they give are not necessarily accurate enough, we are in the process of developing models for classification. So just like before, there are many models to choose from with disadvantages and advantages. After choosing the model, however, there are still challenges that must be addressed regarding the data to be used itself. As you may know, real data is not as easy to work with as people would hope, both in terms of availability and even transparency. And this is especially important to know because everyone can make use of great data, but the challenge usually lies in achieving as much as you possibly can when the data isn't perfect, which will be 99% of the cases. So in line with this, there are many recommendations. You should usually work with data that you can reasonably expect to find in SCADA systems. I mean, for example, panel level data is generally rare. Usually you find a string level or inverter level. And after getting the data, you also need to know exactly what the data means. So it means a little bit of coordination with the teams on the field, because sometimes certain components are already, the outputs are being adjusted to take into account the temperature, and as such, you need to know that the component is doing it at that level. So basically summarizing, after understanding and getting the data ready, we can develop the forecast and classification models, and we'll have our workflow ready to supply the information to the O&M teams. Speaking of which, it's important to remember two things when using these machine learning results. Again, it's important to interpret and understand what these results actually mean. And secondly, it's also very, very important to find ways to translate these results into actions. This can be done in a variety of ways, some of which are being developed within Orion. And this is actually something that you heard previously from Tatiana. Two distinct yet complementary approaches are being developed. Again, firstly, the large language model, which can help O&M teams get intuitive access to insights and recommendations, and the maintenance decision support system, which will give more so direct actions which allow O&M teams to maximize ROI and minimize LCOE. These goals are also represented by the Orion project KPIs. For the algorithms for fault detection is predicted to achieve an accuracy above 80%, which will allow us to reduce downtime in at least 5%, and the time to intervene in some O&M actions by 5%. These percentages are more so in the short term because they are expected to increase as the software evolves. So all in all, we expect increases in energy production in at least 5% and cost reductions of at least 20%, all again in the more so short term. This shows that technological developments really are in service of a greater tangible goal in improving operational efficiency in renewable parks. So thank you, and if you have any questions, please feel free to reach me out, and I'll be glad to be in touch. Thank you.
Thank you, Miguel. Up next, we have Anya from SINTEF. Anya, can you take control of the screen?
Yeah.
Okay, awesome.
Okay, I hope you see the first slide. So this is, I'm from SINTEF, and this is work I've done together with my colleagues, Tony and Leah. And the work of the sensor technology development is very closely related to our use case from Sigma Energy. Sigma Energy has a wave energy converter. And we are working on developing a method to monitor the structural health of this wave energy converter. And if you think a wave energy converter, it sits out in the ocean. If you have normal conditions, under the normal operation conditions, it can handle the waves very well. But it, of course, also has to withstand wave heights and winds that are significantly higher in storms. So it's very important to ensure the integrity of the structure. And that's why we're trying to develop methods by using accelerometers, so vibration measurements, to look at the integrity of this wave energy converter. What does this mean? No. So structural health monitoring, we're interested in looking at the modes of a structure. And if you think you have a guitar and the guitar has different strings with different thickness, and you draw on one of the strings, it will vibrate and it gives you a sound. And if you take another string that has a different thickness, that gives you a different sound. So in that case, it's the thickness of the string that relates to the different frequencies and how the string vibrates. And that's basically what we're doing here as well. We're putting accelerometers on the device, so we're not just listening to it with our ears. And we're recording the vibrations of the system and are looking for variations in these vibrations. The wave energy converter, it's a floating device. So can you see my mouse? So you have these floating elements here, and they are pulled down to the ocean floor with cables. And then you have this part in the middle that is moving up and down with the waves and generating energy. And together with the partners from Sigma Energy, we have identified two very critical points of this wave energy converter. One part is these tension cables. So here on the right, you see simplifications of the device as console models, numerical models. And you have these cables that go down to the ocean. And if one of them breaks or multiple ones, it can, of course, in the worst case, happen that the entire structure just sinks. So it's very important to know when these cables get destroyed. The other part is the power takeoff. So when the platform moves up and down, you have this rack that moves up and down, and that then generates the energy. And if parts of this rack gets destroyed, so the teeth that sit on it, then you can't take the power off anymore. You're not generating energy. In this presentation here, I'm, however, concentrating on the tension cables and the measurements we've done on them. The first step in analyzing was for us to build a numerical model. We're using COMSOL multiphysics for this. And the challenge here is that it's a fairly large structure. So to be able to model the entire structure, we had to optimize the model, and we used different parts like beams. So these parts in between are modeled as beams, and then the floating elements are modeled as shells. That means that you're not generating a very thin wall, but you're making a surface and then you're just giving it a thickness. That's more efficient when you try to do finite element modeling, and the model doesn't take as long to run. And we use this then to look at the eigenvalues and the modes of the system. So that means, how does the entire system vibrate when it gets excited by waves? And these are a few examples. So the first one is a mode where the entire structure moves up and down. So all these cables they are put under tension, and then it's released again. And this has a frequency of 4.8 Hertz for the model we used here. And then you can see for higher frequencies, this is an example with a frequency of 96.8. We have this one tension cable here that swings as half a wavelength. And then for even higher frequencies, we get this movement, or these modes, where you have a nodal point here in the middle. So you're interested to see these different modes. And then the idea behind it is that once something starts breaking, this will change the vibration behavior. And this would mean that the frequency of this mode would change. And that's what we're really interested in. We're interested to detect a change in these frequencies that can tell us something about the state of the structure. It doesn't only help you if you only have numerical models. So Sigma Energy, they carried out a lot of tests in a wave basin. And I think I can start this video. This is not the model you see here on the right, but it shows you very nicely how this little basin works with the platform, and you can generate waves. We did tests, I think, for 2 or 3 minutes normally. Then it gets very chaotic in the test basin, and then we can analyze the data. The model that was used for these tests to look at the tension cables is the one you see here on the right. So you have the floating elements, then you see the tension cable that goes down to the bottom, and the accelerometer that sit on top of these floating elements. So we have one accelerometer on each of these floating elements. And the experiment was carried out in 4 phases, and that's really the really nice thing about having a test basin. You can really test different damage states. So in the first case, we have that all the tension cables are intact. And then in the second phase, we have one cable that's slightly damaged. In the first phase. In the second phase, we have strong damage on one of the cable, and in the third phase, that one of the cables is removed. And all these phases and tests were carried out for different wave heights and different wave periods. So like in the ocean, you would expect different wave heights and periods over time. So we wanted to see the effect of this. On the right side, you see the power spectrum from one example, from one accelerometer for all the 4 phases. And what we're looking for is differences. So if you, for example, look here around 10 Hertz, you see that for the first 3 phases, you see a very clear signal that then disappears. This is, of course, only one example. So what you're really looking for is like characteristic changes in all these different tests we've carried out. To analyze this data, we're using something that's called operational modal analysis. It's a method where you use the data to derive information about the mode. And one important assumption in this is that you have a stochastic broadband signal. So in our case, it's the force of the waves that we assume is an ambient noise source. And then you can use this method to derive your eigenfrequencies and your modal shapes. So this is just an example from a review paper. You have a structure. This is a method that's been mainly implemented for like large buildings or bridges. So you have your structure, you have some kind of monitoring system, and then you do this modal estimation where you make the assumption that your data is a high dimensional space, and you then identify the modes as a lower dimensional subsurface within this. And you use singular value decomposition for this. And then the important thing is that you're able to track your modes. So once you've identified these modes in your system, you need to track them over time, because that's what we're really interested in, right? We want to see when we see a change in these eigenfrequencies in these modes that we can then link to damage. We did some tests, and this is just one example for the 4 phases. And what you can see here is, so we split our data up in 30-second windows and did the analysis for these 30-second windows. And each dot then indicates one mode. And the dashed lines, that's when we can track these modes over longer time. And what you can see here is that we identify a mode around 10 Hertz, and then we have these 3 or 4 modes between 15 and 25 Hertz, and then around 40 and 52 Hertz in case of the phase where all the cables are intact. And then it looks fairly similar in case of the first phase. So where we have slight damage, we still have this mode around 10 Hertz. And then the 3 modes around 20, we can't really detect in the same way the mode around 25 kilohertz here. it looks fairly similar as well for the second phase for the lower frequencies. However, we detect a few more modes between 30 and 40 kilohertz. And then in the third phase where the cable is missing, we can see a clear shift of these three modes that were clustered between 15 and 20 hertz. We detect three modes here, but they are really close around 20 hertz. And then we have one around 15 hertz. So it's these kind of variations you're looking for that you can then use to detect damage in the structure. And that is very much work in progress at the moment. So we are working on making use of this technique of the operational modal analysis and identifying the most significant modes here in this wave energy converter to take this as information further. Because the idea is, as with all the different analysis in the ORION project, we want to do the data analysis. We want to get the information about the state of health of the structure out of the of our vibrational measurements. We combine this with the numerical modeling, and then this information is supposed to go into the graphical digital twin by Augment City. And the idea is to have a system like you see in this image, that you have a farm with different wave energy converters, and you can get the information about the state of health of these different systems, and then you would be able to click on it and get more information about the different damage of the system. Thank you.
Thank you, Anya. Up next, we have a speaker from Sigma Energy, David Vogt. David, can you take the control of the screen?
Yes, I am David Vogt. I'm the director of Sigma Energy. So we are talking about offshore wave energy converters. Now, Anya talked about the how. I am here to tell you a bit about the why. A quick background check. So why wave energy? We know it is an abundant resource. There are potential locations for deployment all around the world, as per the map on the slide. It has a broad potential for use. You can use it as a main, let's say, electricity supply together with the storage system, supplementary supply, autonomy for different, let's say, offshore fish farms and so on. You can use it for off-grid systems, distant shores, meaning remote islands with no access, direct access to the main grid, and also for floating laboratories and so on. And at this stage in the world, we must not forget about offshore data centers and the tremendous use of electricity by AI, the two letters that keep coming up in almost every sentence these days. So our technology is a point type absorber, so wave energy converter. We designed it as a tension leg platform. Because of its secure and stable deployment and operation. It is based on 6 tendons. It has a mechanical PTO system, roughly a very, let's say, a very simple one, although it is not quite that way. The tension leg platform is designed for deep sea operations, so for installments usually above 40 meters of depth. And we're also right now looking into near-shore deployments on a monopile system. This is a short video representing the 30 kilowatt device that was deployed in Montenegro in 2022. And this is what basically visual monitoring looks like. So we use cameras, different ones, to monitor the basic health of the system. This is, let's say, one internal camera next to the generator. And we also had some offshore, so underwater cameras to monitor the sea life around the device and also the basic operations. And this is data monitoring in real time. So we have several sensors monitoring all kinds of things, and the data is then stored for post-processing but also some things can be noticed also in real time. So the system is designed, it works, but what about the maintenance? Miguel talked about different, let's say, cases of faults. I'm talking a bit more about the type of maintenance. So we are talking about planned maintenance, unplanned maintenance, and immediate one. Planned, as you can imagine, is expected, and components are serviced or replaced based on some threshold, something that basically prescribed by the manufacturer. And this is the thing that you can plan out, and it costs the least, so to say, compared to the other two. Unplanned is when you have some gradual degradation of materials, some mechanical fault, electrical fault. That's not, I mean, that you must replace soon, but it's not critical. And immediate is the critical. So where you are facing severe damage and also potential loss of device or even loss of life. So what happens with planned? So components behave as as we expected them to. Replacement is ahead of any major fault. Everything happens according to maintenance plan. For example, a bearing that functions normally is replaced during regular maintenance. That's it. Unplanned is when a component shows some, let's say, expedited sign of wear, and an unexpected service must be scheduled. The deviation here is usually gradual, so you have some time, such as, for example, a friction clutch that starts to go south a bit and you need to replace it sooner than predicted. Immediate is the big issue. So the main problem, especially with offshore structures, when you notice the fault, it may already be too late. For example, such as Anya said, if a mooring line breaks, you need to do something immediately and hope and pray for the best. This is a basic diagram of faults. So just to maybe graphically see what I'm talking about. So we have the planned fault, or basically the planned maintenance, which is light blue, the unplanned in orange, and the dark blue in immediate. So as you see, in the case of the immediate, let's say, situation, you practically have no time to react. Sometimes you have just about enough time to get things sorted, and sometimes you simply do not. What can we do? For planned, not much, because everything is good. For unplanned, if you have something scheduled soon, you include that component for the next maintenance or the next access, and hope you can fix it in time. Otherwise, you actually need to schedule a separate maintenance for this particular component. And for immediate, you either, if you have the option, engage a safety mode or shut down parts of the system or the whole system and hope for the best. But what if we could move these things around a bit? So what if we could make immediate, let's say, a request for service unplanned and unplanned planned? That's what we are talking about. So we are talking about faults that can be detected earlier than with, let's say, existing or standardized methods. So what if we could detect big faults when they were small and dangerous ones when they were still manageable? How? There are several ways to do that. So one is to use the sensors that are already on the device. It is a offshore laboratory as is, and try to analyze the data and find what's wrong. You can use dedicated sensors that you install specifically for detecting faults, or you can go all in and use all available data and do some real-time analysis as well as post-processing. Maybe also develop a learning algorithm to detect faults, and this is what the ORION project is focusing on in the sense of Sigma's technology. So how are we getting, where are we getting to? with Orion, we are starting with the laboratory setting, so with a controlled environment, using wave data, using dedicated accelerometers, as Anya explained before me. And we're using that to develop an algorithm, so an idea how to detect faults early on before they are noticed by individual sensors or even visually. Next step is then to test this in a real environment, so in open waters where we cannot generate the waves, but we can only, let's say, measure them. And then the final stage is managing commercial farms, for which part of it is already being developed under Orion, that is the graphical twin interface that Tanya also mentioned before me. So here we are talking about managing hundreds of devices and having the benefit of the graphical twin to identify and to see immediately issues and how severe they are. So from green through amber to red, and to assign service replacements and shutdowns accordingly. Why are we doing all of this? Well, basically, we want to detect faults before any major damage occurs. We would like to fit unplanned maintenance into regular intervals. But overall, we want to better predict the lifespan of components of the whole system, its availability, as well as durability. The real benefits, however, is that we can prevent a major catastrophe or even avoid the loss of life. And we can substantially reduce the cost of what still remains an expensive green energy solution. Keep in mind that offshore structures are exposed to extreme conditions. They are not always accessible. They can break, sink, or worst case scenario, go adrift and cause major damage. So yeah, thank you.
Thank you, David. Up next, we have a speaker from our sister project Interest. We have Dr. Benjamin Adrian from Fraunhofer ITWM. Benjamin, can you take the control of the screen?
Yes, sure.
Yeah, thank you.
So thanks for having me. My name is Benjamin, and yeah, as announced, I'm from the Interest project. I'm working at Fraunhofer Institute for Industrial Mathematics. It's and yeah, I'm going to talk about something which is quite related to the problem we heard just before, predictive maintenance. So to keep maintenance engineers working inside the plan. Some small words about us. So we are a mathematical institute, but we see mathematics, or we apply mathematics as a core technology, bridging from the physical real world to the digital world. And our tools, or our domains we are working at, is modeling, so explaining complex processes and systems with mathematics and physics, and also machine learning, of course. We simulate with these models, for example, predicting the remaining useful life. And we are optimizing, for example, set points in, let's say, control scenarios. And on the right side, right bottom, you see a simulation of the remaining useful life, which we did for a pump system. Yeah, in Interest, we apply these technologies to systems of renewable energies, which are by nature quite heterogeneous. And we want to combine all these control scenarios to keep these systems running, to combine these with maintenance strategies, and to find best points of maintenance actions to keep to keep these assets alive, and to have a best plan for necessary maintenance actions to, let's say, optimize the remaining useful life in the future. So, and basically this calculation of the remaining useful life, we do some mathematical formulas, which I do not present today because of the lack of time, but the idea is to dive into different stages here. So for example, the green stage here on the left side, it's the infinite life, your endurance limit, everything's fine, the structural health is good, and you can say, well, this asset works as intended. And then you have kind of a change point where some crack occurs, and then your clock starts running, because now you enter the stage of a finite life and you only have a limited amount of cycles which you can keep this device running. And this gives you also a time limit of your maintenance action, which we just heard before. And here, for example, you see an exponential acceleration of the remaining wear you have until you're reaching a point where you really have to repair and to do some action, otherwise the thing will break. The goal is, of course, to explain such a degradation scenario, this curve with mathematics, to learn it, for example, from data. And the goal is also to keep engineers to work on schedule, to have reliable assets, reduce downtimes, and also to remove all these avoidable downtimes, because you're observing, you do a condition monitoring, and you should be able to plan outstanding maintenance activities to let's say lower this curve here, this health indicator, which we call it. The challenges or the tasks under the head of this remaining useful life domain, we tackle 3 of them inside the interest project. So the first one is you're running your device in a steady state operation. For example, this pump, it keeps on pumping in the same state, but and everything's fine. And then something is changing. This kind of anomaly, the structural failure, you want to detect as early as possible, because after that, your exponential degradation starts beginning, and your clock is running, of course. Yes. So this is one task, to observe the point where something is changing in your stable system happens. The second thing is, of course, nothing is in such a steady state in reality, because you're doing maintenance. For example, you're cleaning, you're refueling the oil, for example. You interact with your asset, so you have these kind of tooth chain patterns in your health indicator, and models should cope with that. They should deal with that and understand what's happening here. And this is good impact or a good result if they can explain it, because this means that you can calculate your impact of your maintenance action to the health indicator. So you can really say, I made it better, for, let's say, 50 degrees, which is quite good for the maintenance engineers, to give them a good feeling. And the main challenge is how do we deal with assets that are run under varying operations, for example, different load points, a pump which is accelerating, decelerating, for example, or vehicles, are a very good example. No vehicle is running in a steady state. You're accelerating, you're braking. So everything's changing in every situation, and also models should deal with that and find out how these health indicators are influenced by different loads. So in interest, we are extending a project management where we have a straightforward, let's say, process, starting with we collect measured data from the system beforehand, which we tried to understand the physics and the operation points, of course. We try to identify these sawtooth patterns, in the collected data, and as soon as we see them, we try to stabilize the trends, so to smooth the trend curves in between these sawtooth patterns, and then build a model on that and integrate it into a planning tool, which is maybe even the most important thing that our customers can use it. OPC-UA, for example, is something which is quite simple doing that. So having kind of a digital twin system for example for this pump, an OPC-UA server which exposes its health indicators as OPC nodes, which you can track in your condition monitoring systems, in your dashboards or whatever. So this is our general process, and we did manage, if everything's fine in the data, to come from the first step to the result in 3 months. But most of the time something's missing, and we have to fill this gap in the project. So we say from 3 to 6 months, maybe a bit more. Let's say how complex it is, but it's possible to find out these models and to apply these, for example, in such an OPC-UA. So, which is for our understanding quite important to tell, because predictive maintenance is still a buzzword, in the community, and I've seen running systems very rarely. So we have 3 examples where we could really come to a successful end, where we managed to find such a health indicator, to find a model which explains it, and to do good prognostics. So one is, for example, for these pumps, the green lines here, the vertical lines, these are the maintenance activities. And this health indicator, it's decreasing, or in this sense, it's increasing because of the leakages. It has to turn faster and faster because of the leakages, to hold the throughput. And the second example is a pallet gasifier. It's wood pallets are turned into wooden gas inside of this gasifier, and there's a carbonization process at the boundaries happening, which ends in a state where it has to be cleaned. And we could do prognostics to say, at this point in time, you have, let's say, 36 operating hours left until you should clean it. Otherwise, the gas you're producing, it's degrading in its components, for example. And the third thing is here a ball screw, which is decreasing in its preload under load and under time. And it was quite interesting to see that this health indicator follows a linear degradation here. I thought it would surely be exponential, but it was linear. Sometimes sometimes they are simpler as expected, but not very often. So that's it. So I hurried a bit through my slides because we are lacking a bit of time, I think. And if you have any questions, just come up, talk to me, write me an email. And thank you for your attention.
Thank you, Benjamin. Well, we have come to an end of all our speakers. Thanks to all our speakers for their very insightful presentations today. We will now, well, thank you everyone once again. And as I said, we have our next session next Monday. Please do register. Okay, bye everyone.
Thank you.
Thank you.